In this lesson, we are going to be talking about piecewise functions. I have puzzle pieces as my icon to trigger that when we're talking about piecewise functions, we're talking about functions that are defined in pieces. So our goals for this lesson are to understand piecewise function, to find values of piecewise functions, and to graph piecewise functions. So to get started, I'm going to give you some bullet points about piecewise functions. On the next slide, I'll show you an example of a piecewise function and then talk about these three bullet points as it relates to the example I have. So a piecewise function is defined in pieces, okay? There is more than one output formula for different parts of the domain. So for instance, when we talked about functions before, we had one output formula like x plus 2. With piecewise functions, there's going to be different output formulas depending on what part of the domain we're talking about. And then these pieces, or these outputs, behave differently based on the input value. Let's take a look at a piecewise function, okay? And I have those three bullet points I just talked about at the top. The piecewise function is at the bottom, so we have f of x, so this is one function whose name is f, okay? That's what we'll call it. We have one piece, two piece, so there are two pieces in this piecewise function. There is more than one output formula for different parts of the domain. So this part of the domain is, so this output, x plus 1, is only the output formula for x values that are less than or equal to 0. This output formula, x plus 1, only if x values, only if we have an input of x less than or equal to 0. The second output formula, x squared, we only use for the part of the domain for x greater than 0. Okay, so something you can think of is this could be thought of as y equals over here. So these are our outputs. And this tells us when we can use it. So the inputs, or the domain, tells us when we use what output. And the pieces of the function behave differently based on the input value. So for instance, if we are dealing with values less than or equal to 0, this is in the form of y equals mx plus b. This is going to look like somewhat of a linear function, okay? For the second piece, we have an x squared. If x is greater than 0, this is going to be quadratic. So we're going to have some portion of a quadratic function for that piece. Okay. So now let's do an example, finding values of a piecewise function. So we have a piecewise function, f of x equals x plus 3 when x is less than or equal to 1, and 5 minus x when x is greater than 1. So you might see different words here. You could see if, when, or for. They all mean the same thing. Whatever is in line with the output for the domain, that's what you use in order to determine when to use that. Okay, this should be called g, okay, because I'm looking for values of g. Okay, I had to retype some of this and I didn't catch all of those little things. So first we're finding g of negative 2. So negative 2 is our input. So what we do is we look at which piece corresponds to x negative 2. Our options are less than or equal to negative 1 or greater than 1. Since negative 2 is less than or equal to 1, we're going to be using x plus 3 to evaluate, to find this value, okay? So we plug in negative 2 for the x, plus 3, and we get 1. So g of negative 2 is 1. For the second one, we're inputting 6. Is 6 less than or equal to 1 or greater than 1? 6 is greater than 1, so we would be using the second piece. Okay, and then for g of 1, we have to be careful. The top piece is for less than or equal to 1, so the top piece, the domain includes 1. The bottom piece, or the second piece, this is greater than 1. So this does not include 1, but it includes like 1.00001. Okay, so to evaluate g of 1, we have to look at the domain that includes 1, which is this first or this top piece. So we have 1 plus 3 is equal to 4. Okay. Let's do another example. So this function has three pieces, 5x plus 1 for x less than negative 2. We have negative x plus 4 for x greater than or equal to negative 2, less than 2, and then negative 1 for x greater than or equal to 2. Okay. So for part A, f of negative 3, this falls, our options are less than negative 2, in between negative 2 and 2, or greater than 2. So this one goes with the first piece because negative 3 is less than negative 2. Okay, so we would have 5 times negative 3 plus 1, which equals negative 15 plus 1, which is negative 14. For part B, we have negative 1. We look at which piece. -1 is not less than -2, nor is it greater than or equal to 2. It falls in between -2 and 2. And the way I'm determining that is if you plug -1 in for x, remember this is our input, this is true. Okay, so that also is what tells us what piece to use. Okay, so we are going to use the second piece. So there's a negative already in front, and then we are plugging in -1. So this becomes 1 plus 4, which is equal to 5. Okay, for part C, for f is equal to 4, we look at which piece to use. 4 is greater than 2. So we're going to use the bottom piece. Now notice that this does not have an x value in the output. Okay, this is like y equals -1. And if you remember the graph of a horizontal line, it lies flat like this, and y is always -1 for the domain. So in this case, f of 4 is just -1. Don't take the 4 and multiply it by -1, add -1 to it. Our output there is just -1. So for any input greater than or equal to 2, so for 100, f of 100 would also just be -1. Okay? And for that last one, for f of -2, we have to find the x values, or the inputs that include -2. And in this case, okay, x is greater than or equal to -2. The one above it is only less than -2, does not include -2. So we would be plugging this into the second piece, which is 2 plus 4, which is equal to 6. Okay. Next, we're going to talk about graphing piecewise functions. So you're going to graph each piece on the same coordinate plane. When there is a greater than or less than symbol, so not an or equal to, you do want to see what the function would be there, but on the graph we're going to use an open circle instead of a closed circle, or filling in the function there. Okay, so let's see what that looks like. So graph the function. So f of x equals x plus 2 for x less than or equal to 0, and f of x equals 2x plus 1 for x greater than 0. So we'll start with the top piece. I'm going to divide this into 2 so I can plug in values. You have different options here. So I'll show you one option on this slide, and I'll show you another option on the next slide, but know that what I show you on the next slide applies to this slide and vice versa. So for x plus 2, the first value, so these points right here are called transition points. This is where the graph is going to change behavior, or where the outputs behave differently based on the domain. So when I graph piecewise functions, I start at the transition point. So for x plus 2, I'm going to start at x equals 0, and if x equals 0, I plug in my input, and y would be equal to 2. Okay, now it's tempting to try x is equal to 1, but remember that for this piece, x has to be less than or equal to 0. So now I'm going to go to -1, and if I plug in -1, y is equal to 1, and maybe I'll do just one more. Let's try x is equal to -2, and y would be equal to 0. Okay, so since at this endpoint at x equals 0, y equals 2, this is going to be a closed circle because this includes x equals 0. Okay, so we have 0, and then y is 2, so I have a closed circle here, and then -1, 1, and then I have -2, 0. Okay, and this is going to keep going. This includes its x values less than or equal to 0. Okay, so this is going to keep going. Okay, so that x values are getting more and more negative. So this is what this first piece looks like. Okay, the second piece, 2x plus 1. Remember, we're still going to plug in this 0, but whatever we get, we're going to put an open circle there on the graph. Okay, so if we plug in x is 0, we get y is 1. If we plug in, now I'm going to go up, x is 1 because this is values greater than 0. If I plug in x is 1, I am going to get 2 times 1 is 2, plus 1 is 3, and I'll plug in one more. Okay, so at 0, 1, I'm going to put an open circle. And then at 1, 3, 1 is included because it's a value greater than 0, 2, 1, 2. And this is what this piece would look like. And again, it would keep continuing on because it's for x greater than 0. So it includes values like 10, 15, 100, 1,000. So the graph needs to continue on. Okay, and so this blue is for the second piece. Our next example, graph the function. So this is another way, I'll show you a different way to approach these problems. So we have f of x is equal to negative 1/2 x for x less than 2, and f of x is equal to 3 for x greater than or equal to 2. Okay, so for the top piece, this is in the form of y equals mx plus b. Be very careful that with these problems you don't necessarily start at the y-intercept because it may not be part of the domain. Okay, so we're going to plug in 2. Okay, I always plug in my transition points. This gives me negative 1. So at 2, negative 1, there's an open circle. And then what I'm going to use is my slope here. Okay, now I have to be very careful which direction I go. I can either go down 1 over 2, but wait a minute, that's x values greater than 2. So instead I'm going to go up 1 to the left 2, up 1 to the left 2, because this line still has to have a negative slope, okay, so it still needs to be going down. So my next point, up 1 over 2, up 1 over 2. Okay, so the other way to do this rather than plugging in the points is to use what you know about the functions we've talked about in the class. Okay, for the second piece, this is for greater than or equal to 2. When x is equal to 2, y is 3. 1, 2, 3, and there's a closed circle there because of the or equal. And then y is always 3 for x greater than 2. So we're going to have a horizontal line that starts at x equals 2 and then keeps going as the x values get bigger. Thank you for watching. If you have any questions, feel free to reach out to me.